Good morning, Amherst. Today is Thursday, April 16th. So we had some homework on this last night. This is our KSP worksheet. I want to go over, we're going to finish that today. So we're going to start with number 5 on the next page. And this worksheet, there's a lot of math involved here, so you probably want separate paper. But here we're going to talk about the ion product. Now the ion product, it is the same math, the same formula setup as KSP. So KSP is pretty much the same thing as the mass action expression, which is the same thing as the ion product. Basically, you're saying if I had this many ions mixed with this many ions, would this mass action expression called the ion product meet or exceed KSP? And if it does, that represents an impossible situation. KSP describes the most possible solute you can dissolve. KSP describes a saturated solution. So what happens is you do a comparison, and the take-home message here is if the ion product is greater than KSP, then a precipitate will form. Okay, that's the take-home message there. So let's go over, let's see, we've got 1, 2, there are 4. We'll do 2 of these problems, and you'll have 2 for homework, okay? That's pretty reasonable. All right, so we're going to start with number 5. And it says you've got 0.0065 moles of Pb plus 2 ions, and they're added to 0.0015 molar sulfate ion solution. So basically, they didn't tell you who the partner was here, but if you put these ions together, you would get PbSO4. Now table F would say, well, sulfates are generally soluble, but there are a number of exceptions, and lead is one of them. So here are sulfates, and they are soluble, but not with lead too. So this is not a very soluble compound. Table F would call it insoluble, but we know that everything dissolves a little bit. So if I had PbSO4 solid in water, I would have Pb plus 2 ions, aqueous, and SO4 negative 2 ions, aqueous. And my KSP expression, which is basically the same math as I would use for Q, the mass action expression, which is in this case called the ion product, is simply the concentration of Pb plus 2 times the concentration of SO4 negative 2. So you had 0.0015 molar SO4 negative 2. That's a concentration of sulfate of 0.0015 moles per liter. That's what that means. These brackets mean the same thing. And when you add 0.0065 moles of Pb plus 2, maybe they had a solid PbNO3 taken twice or something like that, the volume of solution doesn't change. They didn't say you added a solution, this just says you added moles. Okay, so I guess you could say then the concentration of Pb plus 2 is equal to 0.0065 moles per liter. That's a bit of a stretch. I don't like the way this question is worded. How did they actually add that? I don't know. They didn't give you enough context, but that's fine. But you have both of your concentrations So you say, all right, well, the ion product in this case, if I add these things together, is going to be this one times that one, which is simply 0.0065 times 0.0015. Hello, tungsten. You're feeling your oats again, huh? Multiply those together, and that's about 9.8 times 10 to the minus 6. In the second part of this question, they said, fine, is there going to be a precipitate? So this is my ion product. Well, KSP, they told you in part 2, is 1.6 times 10 to the minus 6. 9.8 is bigger than 1.6. My ion product is greater than KSP. Therefore, yes, a precipitate will indeed form. You've exceeded a saturated solution. There's no way that solution can hold that many lead ions in the presence of that many sulfate ions. Some of them will precipitate out. Okay, so that's number 5. Number 6 is a fairly similar problem. That's part of your homework. Let's move to the next page. Let's do number 7 together, and then you'll have number 8 for homework. So number 7. It says you've got 200 mils of something that's got 1 molar hydroxide, and you're adding it with 300 mils of something that's got 7.5. Let's add a 0. Let's keep 3 sig figs. That's 3 sig figs. That's 3 sig figs. That's 3 sig figs. Why'd they give us 2 here? Put a 0 here, please. Please add that. Maybe during this quarantine I will revise every worksheet. Clean up the sig figs. All right. So basically you're saying you've got this beaker here. This is a more realistic scenario anyway. And you've got 200 milliliters. And it's 1.00 molar. They didn't tell me what it was. Maybe it's sodium hydroxide. Who knows? Maybe it's potassium hydroxide. But hydroxide's the interesting ion that we're interested in. And you're going to mix that with another beaker. You've got, in this case, more volume. You've got 300 milliliters. And it's got 7.50 times 10 to the minus 4 molar magnesium ions. Now, magnesium with hydroxide, once again, if I were to look at table F, hydroxides are generally insoluble, and magnesium is no exception. So, MgOH twice would be an insoluble or mostly insoluble substance. So if I had some solid of that and I was in water, I had Mg plus 2 aqueous and 2 OH minus, going off the page here, sorry, aqueous, I could say KSP, which is the same thing as Q in terms of setup, which we're calling our ion product. That would be Mg plus 2 times OH minus, but in this case it's squared because of the 2. But the deal is, when you mix 200 mils of one solution with 300 mils of another solution, your total volume increases. So the final volume of solution is 500 milliliters. Well, that's half a liter. All right, well, let's figure out how many moles of ion we had for both of these, and then we'll divide by our 0.5 liters, and we'll get a concentration for each. So if I handle OH minus first, I could say, well, I had tungsten. I'm busy. 200 milliliters, that's 0.200 liters. And it was 1.00 moles per liter. So that's 0.200 moles of the hydroxide ion. So if I want to know my hydroxide ion concentration in the final solution, I'll say, well, it was 0.200 moles. My final volume of solution was 0.500 liters. 0.2 divided by 0.5, that's 0.400 moles per liter for hydroxide. Let's go back and handle magnesium now. So you've got 300 milliliters. That's 0.3 liters. And its concentration was 7.5 times 10 to the minus 4 moles per liter. 7.50, we added that 0. So that turns out to be, I could plug it in my calculator or look at the solution I just did. Magnesium turned out to be 4.50 times 10 to the minus 4. Check my math here really fast. So 0.3 times 7.5 second E negative 4. Yeah, 2. Sorry. I have to take this whole thing and divide it by my 0.5 liters of solution. I apologize for that. These liters canceled, so now I have moles over liters. So that number is, the top number, the numerator is 2.25 times 10 to the minus 4 moles of magnesium ions divided by half a liter of solution, just like I did here. And that's 4.50 times 10 to the minus 4. Apologize for that little confusion there. Let me just reiterate what I just said there. I went to my hydroxide. I said I've got 200 mils of solution. That's 0.2 liters. And its concentration was 1 mole per liter. I had that many moles, and I divided it by my final volume of solution to come up with 0.4. I had 300 milliliters of the magnesium ion. That's 0.3 liters. It was 7.50 times 10 to the minus 4 moles per liter. That gave me 2.25 times 10 to the minus 4 moles of magnesium plus 2 ions. And I divided that by my 0.5 liters, and that gave me a concentration of 4.5 times 10 to the minus 4 moles per liter for magnesium. So my ion product was equal to magnesium ion concentration times hydroxide ion concentration squared, which is 4.50 times 10 to the minus 4 times 0.400 squared. I'll check my math. So 0.4 times 0.4 times 4.5 second EE negative 4. My ion product turns out to be 7.20 times 10 to the minus 5. Part B of the question said, so this is my ion product. Part B of the question says KSP is 1.0 times 10 to the minus 11. Well, that's a lot bigger than that. 6 orders of magnitude. So my ion product is greater than KSP. Therefore, yes, the precipitate, lots of it, will form. All right, so this math gets a little bit into the woods. I don't want you to get too hung up on it in the greater scheme of things compared to what we're going to do with the rest of this unit. This is not as much, but you're going to have two homework problems. You're going to do number 6. Once again, you got the moles, and I'm just going to get you started on number 6 here a little bit. If you take lead plus 2 with hydrochloric acid, you're going to do a single replacement reaction. Hydrogen's going to get kicked out. Now hydrogen is Hofbrinkel. There's our H2, so put a 2 here. So now you've got Pb plus 2 ions and Cl minus 1 ions. So your other product here is PbCl2, which table F would say all halides like to dissolve, but now with lead plus 2. So the compound of interest there is PbCl2. I'll let you take it from there. So you're going to do number 6, and you're going to do number 8, and they even told you the final volume of solution here is 2 liters. Okay, the 2 examples I did are pretty similar, and I've started you on number 6. Ask me questions along the way. Tomorrow we do Le Chatelier, and then we're into Regents Review, practice test, and a test next week. Practice test, it's huge, by the way. I've been making up Google Classroom forms for it. We're going to count Regents Review as a grade, we're going to count the practice test as a grade, and we're going to count the test as a grade. So we've got 3 grades to get next week. Study up. Talk soon.